All right, everybody. So how did those problems go on Thursday and Friday? Well, I don't know. It's number one should have been easy.
Easy until like table.
Three was a lot of work.
Until the table was hard.
The table was hard.
Like the
Okay.
Yeah.
Let me pull up the table. Let's talk about that.
Max.
Table.
Oh, I'm loving your sweater. He's like do something. I hate sometimes we get this book. I still really
All right. So let's talk about number 3. So all this table is for number 3 is just a bunch of stoichiometry. I just wrote it in a really compact way, which turns out is a really helpful thing to do. Anytime you have a reaction happening, you're going to have more than one thing changing concentration or changing moles or changing pressure at the same time, right? So part of what I wanted from number 3 is you to realize that, okay, well, filling out this table is just a stoichiometry problem, right? Because all you have to do is figure out what's going to run out first, what's left over, and then you have to figure out, okay, did I make more of something or did I use it up? Right, so the way it's written here, it says, okay, figure out how many moles you had of everything before the reaction. Did we have any CO2 or water before the reaction?
Mm-hmm.
I mean, I didn't say anything about it, so you can assume that there's nothing there. If there was any pre-existing water or CO2, I would have told you. Otherwise, you're just supposed to assume it's 0. So that means filling out 2 of the boxes is really easy. As soon as we figure out how many moles we have before the reaction, that's filling out this entire first column then. It's just, well, I've got, let's see, what's the information? We have 4 grams and 12 grams, right? We have 4 grams, we have 12 grams. We can just use molecular weights to figure out moles, right? We've done that since, I don't know, probably October at this point. So if we know how to fill out the first part, then after the reaction, all we have to do is figure out, well, we know everything's changing, but each one of them is just changing based on stoichiometry, right? So we just got to, if we know, as soon as we figure out what's going to run out first, then we know what to put for moles after the reaction for that one, right? So in this case, what were the moles for that? It was something like what? I'm not going to try and do it from memory.
Which one?
So let's start with the butane, C4H10.
0.08.
That sounds familiar. Moles, and then O2 was something like 0.032. 375. We got to balance it before we can do anything, though, right? That's going to give me an odd number of H2Os, which isn't going to work. So we're going to put a 2 there. That means we're going to get 10 waters and 8 CO2s, right? And then we have to get our oxygens based on that. 8 oxygens plus 5 oxygens. So 13. That look right? I know I did that really quickly, but you had more time to do that. So if it took you 2 tries, if you started by just balancing everything and then had to go back and double everything, that's what I would expect at this level. Once you've balanced 100,000 combustion reactions, then you're pretty good at seeing, oh, that's going to give me an odd number of waters. I need to double everything before you even start. So let's write this table in a slightly different way. We already have two of the values for that table written, right? The way that's convenient in chemistry to write it is what we worked on Friday, which was those ICE tables, which stands for initial, change, and end. Right, so our initial conditions is what we start with. 0.0688 moles, 0.375 moles, 0 moles, and 0 moles. Everybody with me? All I did was took what we wrote in our first column in this table, and I just transposed it sideways so we can write it underneath the chemical reaction. Right? So it's just a different way of arranging the numbers. The other two rows, basically what we're going to do with this table is the end component is what is the second column here. Right, what do we have after the fact? Well, hopefully you were able to figure out what's going to run out first here. What's the limiting reactant? Even though we have more moles of it, we're using it up 7.5 times as fast, right? So we're going to run out of the oxygen first. If we know we're going to run out of the oxygen first, we can fill in something for the E row, right? At the end of the reaction, we know we have no oxygen left because we used it all up. It's our limiting reactant, right? The thing where these ICE tables get really helpful is actually this middle row. Because we can actually fill out this middle row and turn this into, basically we call it a matrix system. It's basically going to be just a system of algebra equations that all use the same variable. Because we know this is balanced, we know that all of these are going to be changing. We're using up reactants, we're making products, and we know if it's balanced, we know the relative ratios of all of those. So the way to fill out this middle row is we're just going to use a standard variable. What's the standard variable you're used to working with? That's a unit. Just in algebra. If you're doing algebra, you're solving for x, right? So we're just going to fill all of this row in with x. Except it's not the same number for each of these. Basically, we're going to say every time the reaction happens, if the reaction happens one time, how many butanes do we use? How many, sorry, C4H10s? That's butane in OChem speak. We're going to use 2 C4H10s, and we're going to use 13 oxygens every time this reaction happens, right?
Right.
And we're going to make 8 CO2s and 10 waters. If the reaction happens X number of times, how many C4H10s are we going to use? 2X. And are we making them or using them up? We're using them up, right? So we're going to be losing 2X. So where did the 2 come from? Yeah, it's how many moles are in our balanced reaction, right? So what are we going to put underneath oxygen? If the reaction happens X number of times, first off, is oxygen being made or used up? Used up. So is it plus X or minus X? Minus X. And how many X's? 13. It's not entirely obvious why this is going to be helpful yet, but trust me on this. Let's fill out the rest of this row.
Plus 8x.
Plus 8x. It's plus because it's a product. We're making it. We're adding CO2. And plus 10x. How does that help us? If we can figure out how many times the reaction happened, we know all we did with this is we did stoichiometry. We just didn't write it as a conversion. Because all stoichiometry was figuring out if I'm using up this many moles of A, how many moles of B do I make? That's all this did. It took the balanced reaction and it put everything in terms of the same variable. And as soon as we know all of one column, we can solve for X. Because if we start with 0.375 moles of oxygen and we end with 0, and this is the change, we can say 0.375 minus 13x equals 0. That's pretty easy algebra to solve, isn't it? This is what we started with. This is how much it changed. This is what we ended with. So that gives us a way to solve for X. And as soon as we know what X is, we can solve for the rest of these. That's all this table was asking you. It was just having you, instead of solving for X, it was having you figure out, write it as 4 different conversions. Show that all the oxygen is being used up. Show how much butane is, or C4H10 is being used up and how much is left. Show how much CO2 is being made. Show how much water is being made. So for the CO2 and the water, the moles after, that's just a theoretical yield question, right? How much can we make? And how much of the C4H10 is left over, that's an excess reactant question. How much leftovers do we have? This is just a way to do all the math at once. Right? Because all of them are going to be tied to the same X value if we balanced it right and if we filled out that middle row properly. So what do we get for a value for X?
0.0885.
And how many of these sig figs do we get to keep? If I'm remembering correctly, I think that this one actually, we could have kept one extra sig fig here to begin with. So I think we can go to the 10,000th place, to the 4th decimal place. So I think we get something like that. So what is X really representing? It's not anything on its own, right? Well, kind of. It's how many times did the reaction happen? If you know how many times the reaction happens and you know whether something is being used up or produced, that's enough. So that right there, as soon as we know X, we know at the end of the reaction, our moles of water is 0 plus 10x. So it's just going to be 0.289 moles of water at the end. 8 times X is going to give us our value here, which we get what?
0.2.
This one's looks a little bit different because it's a subtraction, but it's just going to be 0.0688 minus 2x. So something like 0.01. Right, so could you have done this without using an ice table? Yeah. It just would have been a whole bunch of conversions and writing out your stoichiometry as a conversion step, the way we're used to doing it, right? So I kind of expected you to be able to get through this and be really angry at me for writing this problem by the end of it, because it was a little bit repetitive and a whole bunch of just conversion stoichiometry to fill this out, right? And then I was going to show you this way to do it, which is just a faster way to do the same math. All right, what was the last question on this part?
Something else.
Oh. Once we have our final moles of each of our gases, it says you've got temperature is 39.1. The volume is unchanged. So still 10.00 liters. What's the partial pressure of each gas and then the total pressure? If we know moles, we know volume, and we know temperature. Getting the pressure for each of these is pretty straightforward because what's the number one equation that you should think of when we're talking about pressures and temperatures and volumes? Fibnert. Because as soon as you know moles and you know temperature and you know volume, all you're missing is pressure for each of these, right? So that was the piece that was a little bit new in part E, was we can do this for individual gases. And that's what we call the partial pressure. Right, so if we want to know the partial pressure of CO2, we take the moles of CO2 and we plug it into Perfnert. Right? So pressure is what we're solving for. CO2, volume is 10.0 liters. Moles for CO2, it's 0.231 moles. R is always the same. Liters, atmospheres, moles, Kelvin. And then we had, what does it say? 39.1 Celsius, which we can't leave it in Celsius though, right? So we made the point adequately. We should do everything in gas laws needs to be in what temperature units? Kelvin. Usually there's at least one joker who says Fahrenheit and have to throw something at him. So good. Kelvin. We're in 39.1. Solve for CO2. Do that with all the other ones. Nothing else is changing. They're all in the same container. They're all at the same temperature. So the only thing that's changing about all your other gases is what you're plugging in for moles. And so partial pressure is just that. It's part of the total pressure. For
like those ones. Should they be?
This one, because we took something that had X had 3 sig figs, right? And then we multiplied by 10. So our answer only gets 3 sig figs. The only place you might, no, none of them are going to have 4 sig figs. Do these gas molecules interact with each other? Does it matter what the molecule is when it comes into figuring out your total pressure? How far apart are these gas molecules? Are they pretty packed in there pretty tightly, or are they pretty spread out? They're really spread out, right? In fact, one of our assumptions in using the ideal gas law was that these gas molecules don't interact with each other. They all behave like ping pong balls that bounce. If they hit each other, they just bounce off and they have no interactions whatsoever. So it really doesn't matter what the molecule is, which is why we can just take our individual pressures, our partial pressures, and we can just add them up to get the total pressure. Or we can add up all the moles separately and then plug it back into PV equals nRT and get our total pressure that way. You should get the exact same answer within sig figs. There might be some rounding differences there. Right, so this was a long problem. And I expected this table to cause a hang up for a little bit. So that we can come in here and learn how to use these ice tables. Right? These, when you take general chemistry, there's an entire, practically a third of the class of general chemistry is on using ice tables. Because turns out in general chemistry, we get into the idea of equilibrium in more detail, which means reaction doesn't actually go to completion, which means you don't actually have any of these end up at zero in the real world. And figuring out exactly what the X value is if none of these goes to zero is a little bit trickier. And you spend 4 or 5 chapters. Literally about a third of the Gen Chem series is how do we do ice tables and how do we solve equilibrium problems? Because what we like to do in chemistry and in sciences in general is we're going to teach you how to do it one way, the simple way. And then next year, you're going to come back and we're going to say, well, that wasn't actually good enough. Now we're actually going to add another level of complexity. And then the year after that, you come back and we do the exact same thing. Every single chemistry class you take that builds on itself, or science class in general, is basically a class of, that was good enough for last year. All right. So, yeah. So if it only wants partial pressures for after the reaction, all you have to do is take this last row or the second column here, plug the moles into PV equals nRT for each of them. So again, repetitive. If you wanted to do it using a spreadsheet, that would be one way to do it, avoiding making it so repetitive. So you don't have to write the same thing out 5 times in a row. And that's not a bad habit to be in. About 4 times, if I do have to do the same calculation more than 4 times in a row, I always go to a spreadsheet. If it's 4 times in a row or less, I might do it by hand on a piece of paper. This is right on the border of where I would think, it's probably worth it to get out a spreadsheet program. Because spreadsheets are really good at repetitive calculations, right? Did you do a spreadsheet lab at the beginning where you did some calculations? Okay. Unfortunately, that's good life skills right there. I don't know of a single job where you won't use a spreadsheet in some level. A single career, I should say. If you start your career as a construction worker, just framing houses, you might not need to use spreadsheets then. But if you get to the point where you're running a crew as a foreman, you absolutely need to use spreadsheets. So that's not a career. I've seen that Netflix show. They don't make that much money, do they? Oh, okay. You could. So how do you think they keep track of? Actually, I think I've seen the spreadsheet in that Netflix special. I think that the coaches, when they're keeping track of who to cut and who to keep, I'm pretty sure they're using spreadsheets to do it. So, perfect. All right. So, apologies for getting this a little bit out of order, but 2 and 4 are both going to be a lot easier if you know how to do an ice table. In fact, I'm not going to do number 2. What I will say for number 2, so this is due on Thursday. So you still have a few days to keep working on this. For the second problem, one of the big things to realize is that pressures can also be plugged in here. Pressures are proportional to how many moles you have. If you know the pressure of something and you know that all of your gases are in the same container, you can plug all of you can basically do this not just with moles. You can do this with pressure units as well. You can't do this with masses. Why can't you do this with mass? Why can't I just say 4 grams and 12 grams? Because it doesn't work like that. It's a good answer. Is it? Basic, because grams, they all have different molecular weights. With gases, good job. With gases, they're all in the same container. If they're reacting, we're assuming they're all in the same container, which means they all have the same temperature and the same volume, which means pressure and moles are really pretty much the same thing. So you don't actually need to know, for number 2, you don't need to know how many moles you have because you know how many kilopascals, I believe it says, right? Acetylene gas turning into benzene.
Do you remember what the total pressure was?
I want to say it's half what you start with. So if we can do this with, I'm not going to work through the whole thing, but we can fill out the first row because we're given 7.8 kilopascals. So you can just say, doesn't even matter if you know the conversion for kPa, as long as you recognize its pressure, therefore you can use it in place of moles. And we know we're not starting with any C6H6. It's not reacting the entire way, but we can still fill out this change row, right? Because we can do it all in terms of x's. How would we fill out, what would the change row be? Minus 3x and just plus x, right? Which means we can at least fill out the end row in general terms. We don't know what x is, but we know at the end, 7.8 minus 3x is how many pressure units we have of the C2H2. And we're going to have x mole or x kPa of C6H6. So I'm going to leave that like that for now. See if you can figure out, given the information in the problem, how do we solve for x? How do we figure out what x is?
You start with Ryan. Where are my pets?
And we'll talk about that on Wednesday.
Are you coming on?
I'll be here on Wednesday this week.
Did you say?
I did. I had a family member end up in the hospital, so I had to be in the hospital at the end of last week. So I apologize for that. They're fine now. But this Wednesday I will be there. It's finals week at the college, which means I don't actually have my lab meetings. So I'll be able to be here on Wednesday. It's a nice thing about college. You only have to meet once during finals week per class just to take a test. So, all right. Any more questions about this assignment so far? We'll talk about problem 4 in more detail then as well. Actually, if you're good at algebra and problem solving, you don't have to be good at algebra, but it does help for this problem. The hint that I'll give for number 4. If you have 2 different reactions happening, for number 4, you have 2 different combustions happening. They're both going to be balanced differently, and they both have different starting amounts of your carbon-based material. If if you have different amounts of both of them and they're balanced differently, you can still write ice tables for both of those reactions, but you're not going to want to use X for both of them.
Why?
Why what? Exactly. So what you're going to want a different variable for the second reaction on number 4. Because the first reaction might happen X number of times. The second reaction is going to happen a different number of times. So if you fill out an ice table for the second reaction using Y instead of X, you might be able to solve your problem. You're going to wind up with 2 variables, which is going to take a little bit of substitution to solve, but it's doable. In fact, that is one of the biggest skills that you get from, I'm trying to think of if I should say from a chemistry degree or just a science degree in general, is the ability to write your own algebra problems and then solve them. It's a good question. It depends on what you define the real world as. Anytime you have more than one thing happening at the same time, you're running a restaurant, you're making cheeseburgers and you're making burritos. And you're both using the same ingredients.
And burritos. Pretty cool.
You guys not been to Chico's? They have pretty good cheeseburgers and they have really good quesadillas.
It's good. It's
All right. Enough practice with this stuff. Let's talk about new stuff.
News. You can drop this on me. You not drop this ball on
It's not nearly as bad as all that.
Are you gonna come to the first photograph?
All right. Let's do some more practice with gas loss. Less stoichiometry, more gas loss. For a few minutes anyway. And then gas laws with stoichiometry.
I think about
All right, so this one's written as a problem. It's a combined gas law problem. Might need to use the combined gas law problem though. We also have all the pieces we need for PV equals nRT. So you can do it in one step without ever actually solving for moles. It's by using the combined gas law form. Because we have all 3 pieces on the left and we have 2 out of 3 pieces on the right. Or we can solve for moles and then we don't need to worry about using the combined gas law. It's whatever you prefer. Dealer's choice. But it's not that much of a choice. What'd you start reading?
Handmaid's Tale.
Oh, fantastic. Don't let the bastards get you down. That's a pivotal quote from later in the book.
Hard read.
Um,
Oh, wait.
Yeah. Well, that's a big part. We'll be-
How we doing, everybody? Is this straightforward?
Is it?
Is this pretty easy? Okay,
I'll discuss it.
plug this in. Keep it focused.
Yeah.
I like a little bit of noise as long as it's on topic. What do we get for moles? Five point,
We must change.
change it into, oops, I wrote Celsius, but I meant Kelvin there. You forget to do Kelvin. This is one of the reasons why it's worth writing your units on R. The other reason that it's worth you writing your units on R is because if you don't, I'm gonna mark points off. No, it's on your conversion sheet. But if you use R without writing the units, I will mark you off a point. So write the units, even though they're meaningless seemingly. They're going to remind you when you forgot to convert from Celsius into Kelvin. So what do we get if we're in the proper units? What do we get for N?
For what? No, it's. No, no.
1.7.
You did something wrong. Thank you.
Is that a reasonable number? 5 liters. How do we know if that's a reasonable number?
We check to see if we equals.
Well, you could do it backwards and see if you got R.
Let's call for it.
If you have everything plugged in, you can also just look at it. 1.05 ATM, 5.00 liters, over 0.08206 liters ATM, mole, Kelvin, 295.2. If we're trying to do this in our head, we want to do mental arithmetic to see if we're even in the right ballpark. That's going to be really close to 5, right? That's R is pretty close to 0.1 if we're doing mental arithmetic. What's 0.1 times 300? 30. So 5 divided by 30. 1 divided by 6. Is that in the same ballpark as 0.2? A 6 is 0.167. 0.2 is pretty close. So yeah, we probably did it right. If you didn't get something reasonable, it might be a calculator issue. Or it might be a units issue. So how do we do with the second part? Now we know everything except pressure, right? It's still just PV equals nRT. If it's a sealed balloon, we can assume that N is the same before and after. It's not exactly true in the real world because what happens to a balloon 2 days after you filled it up? It's definitely not as full as it was, right? There's actually some of the gas molecules inside the balloon can make their way through the balloon membrane, and you actually lose some gas molecules. For the sake of this problem, though, let's assume that N is constant, which means afterward we can still use the same N value. But then everything else changed. Temperature increased to 40.5. Volume went from 5 to 5.05. Once again, we've got 3 out of 4 pieces. Solve for what you're missing. If I picked these numbers properly, the pressure should be a little bit higher as well. But then again, I did just make these numbers up, so it's possible that I misjudged something in there. Pressure is equal to 0.217 times R, 0.8206 liters ATM, moles Kelvin. Times 313.7 Kelvin. All of that over 5.05 liters. Everything cancels out except for ATM.
Lit. That was for lit. Liters. Bro, you're not doing shit. Let's see it. Mental arithmetic.
30 times 0.2. So it's a fifth of 30 is about 6 divided by 5, something a little more than 1. 1.1 or so.
1.106. Oh, that's a zero. Who's the letter? You got some good thinking in that.
Just round everything. So math that you can do in your head. Point 0.1, call R 0.1, call that 300. So that's 30 times 0.2 is the same as a fifth of 30. So 30 divided by 5 is 6. 6 divided by 5 is about 1.1. You just round everything to the math that you know how to do in your head, and then get good at doing fractions and converting fractions into decimals in your head.
Or you
Or you could use a calculator. But you should at least know within an order of magnitude what your answer should be. When I say within an order of magnitude, you should know if you skip a decimal place somewhere and you multiplied by 3,000 instead of 300, you might not catch that unless you're doing at least rough mental arithmetic in your head. You got to do those reasonableness checks. And that'll keep you from getting marked down for calculator errors. Plus, it's also really helpful on standardized tests. Multiple choice tests are a really good place because you can take the SAT without actually even using your calculator because
Who's you?
two of your answers you can rule out right off the bat if you can do this in your head. And if you look harder at the other two, one of them is going to be obvious.
I just through a lot of calculus. You know, if you does this,
Really?
Yeah.
you get the. It's so easy. Just graphing calculator.
It's like plug up to this.
So that is great that you get Desmos. and everything on standardized tests. And I'm not saying don't bring your calculator.
Oh,
I'm just saying it helps you catch when you made a syntax error if you can at least get roughly what it's supposed to be in your head. Okay?
Syntax stands.
It's its own word. I don't think it stands for anything. Syntax is like grammar. Probably comes from.
An abbreviation.
Let me know. Tell me what you find out. All right. Here's an easier way
Easy.
to do a reasonableness check with gas loss.
Don't know.
In gas laws, there's a set of conditions that we call standard temperature and pressure. Standard temperature and pressure, abbreviated STP, is basically saying, okay, well, if most gases are at 1 atmosphere, we chose 1 atmosphere to be 1 atmosphere because that's normal pressure, right? And then they just made 0 Celsius standard temperature for a couple reasons. One of which is because it's really easy to convert from 0 Celsius into Kelvin. What's 0 Celsius in Kelvin? 273.15, right? So if you're at standard temperature and pressure, 1 mole of gas will always equal the same volume. Because if you're at standard temperature and pressure, then you can basically say, okay, plug in 1 for a mole and see what volume that comes out to be. So pressure is 1 atmosphere. We'll call it exactly 1 atmosphere. Temperature is 273.15 Kelvin. N is 1 mole. Again, we'll call it exactly 1 mole. What is volume?
What about, what are the moles? One, shoot. 273 times more. Get the cow, get the cow.
That was not mental.
Okay.
Mental arithmetic. This is a common enough number. I don't want to dishearten you too much. This shows up all the time because this actually gives us a really easy way to convert between moles and liters. If our molecule is a gas at standard temperature and pressure. At standard temperature and pressure, 1 mole of gas is 22 liters. So I started this by saying an easier way to do a reasonableness check. 5 liters, 1.05 is pretty close to 1 atmosphere. 22 Celsius is pretty close to 0 Celsius for the sake of rounding. That's about a quarter of 22, roughly. So it should be somewhere in the ballpark of a quarter of a mole. And we came up with 0.21. So without even having to write the numbers on the board, I knew that 0.21 number was a good number, was a reasonable number, because I knew it was going to come out to be about 1/5 to 1/4 of a mole because I knew this number in my head. In most conditions on Earth, gases are going to be pretty close to STP. In fact, up until the last 50 years or so, 100 years or so. 1 degree. The other reason that 0 Celsius was chosen for a standard pressure or standard temperature is because up until about 1900 or so, it was a pretty good estimate for your global atmospheric temperature worldwide. If you average the annual temperature of the air any point on Earth over the course of an entire year, it comes out pretty close to 0 Celsius. Not exactly, but close enough that they could do this. It's still not far from it. I think that globally, average temperatures are now closer to 1.5 Celsius if you average them out for over the entire year. It's not as close to 0 anymore, so that's not as good of an assumption anymore. But it turns out 0 is not a bad estimate for just if you just pick a place at random in the atmosphere of Earth. 0 is a pretty good estimate for what the temperature is going to be. Why wouldn't we use the average ocean temperatures? Because does the ocean factor into PV equals nRT? Because it's not what? It's not a gas. Why would we use the gas law? We're going to take the average atmospheric temperature, not the average ocean temperature or land temperature. Take the average atmospheric temperature for this. If you've never played around with this website, this is just a fun thing this is an aside. It's relevant to meteorology and gas laws. This is just a real-time map using satellite data of wind speed on Earth. So blue is going to be the slowest. So here's your scale right here. It's also got other cool things. Well, for one, as you zoom in, you get better resolution. So you can see Tahoe, you can see Salt Lake. Don't have a whole lot happening in California right now. We have a high pressure front sitting right on top of California, which is why we don't get any snow for the next week or so, I think. Because what causes wind?
The wind god.
The wind god.
Yeah.
All better known as pressure.
This side. No, that's. Oh, this is lightning.
And actually, I don't think that there was a Greek wind god, was there?
Let's ask you. Yeah. Yeah, you give me an.
Here's the other cool thing it does.
Oh my gosh, hurricanes. What is that?
Ocean currents.
Are those supposed to mean hurricanes?
So this is not wind anymore. This is the ocean currents. So there probably is a storm system there, causing the water to swirl like that.
His name's Nemo. I mean, like a wind god.
This is surface temperature anomaly. Surface temperature anomaly is how hot or cold the ocean is relative to the 10-year moving average. So in other words, how hot is it compared to how hot it normally is this time of year at that location? So what this is showing is that most of the ocean is significantly warmer than it normally is at this time of year in these locations.
Why is that?
Why do you think? Yeah. Basically, if you track this over the last 75 years, it looks like a hockey stick laid on its side. They could actually call it a hockey stick plot. But if you look at global temperatures, I think you have to start back at 1900 to really to see it. It's pretty steady increase since the 50s. Anyway, it's a little bit less relevant, but worth playing around with.
Keep playing.
Earth.nullschool.net.
What?
I can never remember the actual website. I always have to Google real-time wind map or something like that.
How often do you visit those websites?
We have a screen like that that sits out in the commons that we just leave on that website because it's just one screensaver to have. Y'all are too young to remember this, but there was a thing called screensavers because you couldn't turn off your screen because it took forever to turn your screen back on. And if you just left a single image on your screen, it would burn into the back of the screen itself. And then anytime you looked at something else, you'd be able to see what that image was that you left it sitting on. It literally burned into the back of the screen so that you couldn't get rid of that image anymore. So they used to have these things called screensavers, which basically change the image every so often so that you didn't burn out your monitor. It's a weird thing from CRT era.
It was yesterday.
When Windows 95 came out, it was a big deal because it had really interesting screensavers, like this little maze. It would just it looked like it was looked like Minecraft, basically going through a maze, and then it would come back around, and if you waited long enough, you would see the automated process reach the end of the maze, and then it would start a new maze. It just kept going infinitely. All right, let's practice using that 22.414 number. So for this problem, this is our baking soda and vinegar problem. If you really wanted to put it in Minecraft terms, and you could replace grams of sodium bicarbonate with, I don't know, stacks of iron. How many breastplates could you make with one stack? First, you got to take stacks of iron, you got to convert it into bars of iron, and then you can take iron ingots and you can convert it into chest plates, right? That's all stoichiometry is. We're talking about Minecraft. Sorry. If you're not a Minecraft, you're ignoring it.
I get it to another interest.
I derailed everybody with that one. Did not mean to do that. How do we figure out how many liters? Let's think about the phrasing. This is being recorded.
Oh.
They want.
If I ask you how many moles of CO2 is here? If I ask you how many grams CO2 is going to make, we could do that too, right? The acetic acid. Not limiting, so it doesn't matter how much we have. 10 grams sodium hydrogen carbonate. Let's figure out how many moles that is. $23, $24, $36.
67.
Something like 72? No, 84? I think. All right, who's got a calculator out? Give me a number here.
67. 41.
84 works. Give me one more sig fig at least. How many moles of CO2 is that going to make? One-to-one conversion, right? If we're at standard temperature and pressure, so that's enough now. That if we stopped there, we'd get moles, and then we could plug that into PV equals nRT to get our final volume. However, if we know that at STP, 1 mole is 22.414 liters, that's a conversion, as long as we're at standard temperature and pressure. So that's going to save us a step. Now we don't need to use PV equals nRT. PV equals nRT is built into this if we're at standard temperature and pressure. 1 mole of any gas is 22.414 liters. So, mental math trick. 22 and 84. Well, it's about a quarter, exactly. So something like a quarter of 10. So somewhere around 2.5 liters. Yeah. 10 over 84 times 22.414. 2.6.
Oh.
Can't make it up. Well, you could, but I didn't. That's actually it's kind of impressive. Not the 6-7 part of it so much as the over 2.5 liters of gas from 10 grams of baking soda. You take 10 grams of baking soda and you put it in vinegar, you're going to get 2.5 liters of foam, of bubbles. Which is why those volcanoes work so well. You ever done the classic baking soda and vinegar volcano? That's what this reaction is. You can do it at home. Maybe next week.
If you insist, fine.
So none of you ever took any of those Connect camps over at the college, these exploring STEM camps for middle schoolers, anything like that?
Yeah, I don't know if this existed.
Probably not. We actually used this reaction to design rockets out of soda bottles and vinegar and baking soda. You can actually get them to launch into the air pretty well. Not like an actual rocket, but you could get, we hit the ceiling in the lab just by using baking soda and vinegar and then putting it into a soda bottle that directed all this gas down out of the bottom of the bottle, and then which propels the bottle up. All right. Hindenburg. Famously, the cover and inspiration for what classic rock band? Led Zeppelin. Led Zeppelin's early demos were predicted to go over like the Hindenburg, like a lead balloon. They took that as their name for their band because they thought it was such a good description. So this is the actual picture of the Hindenburg, which they took this picture and they processed it, not digitally because they didn't have computers, but that is the cover of Zeppelin 1. It was basically a balloon the size of both of the gyms put together here in terms of volume, filled with hydrogen. Turns out you can make hydrogen from water as long as you have electricity. Hydrogen's actually really easy to make as long as you've got at least 1.1 volts of electricity and as much current as you need. So why did they use hydrogen instead of helium? It was lighter. Hydrogen gas is H2, right? So molecular mass of 2 grams per mole. Helium's about 4 grams per mole. So it's about half, you get twice as much lift from hydrogen compared to helium. So since they were trying to make this was before they had airplanes readily available, they were marketing these as ways to travel instead of taking ocean liners. Well, because look at that picture. What happens when you add hydrogen to oxygen gas with a little bit of heat or a spark? All that happened to the Hindenburg is it got a little bit too close to the docking station and a piece of metal scraped along the outside of the balloon. And it lit the whole thing on fire. I don't think there's any video, but if you ever heard the classic, I think it was Orson Welles, "Oh, the Humanity" radio broadcast was somebody who was on the radio who was a newscaster who was documenting this process. Like, oh, the Hindenburg is docking here in, I want to say it was New York somewhere. No, it was Europe. But basically, and then it turned into this big devastating catastrophe.
It's actually one of the first times that disaster got captured live on video.
So it is.
That's
Oh, so we do have video. Okay.
not video recording because it was a big deal actually.
Yeah. This would have been what, just after the Titanic? It was pre-World War One. It was in the early 1900s.
And Hannah.
37.
In 1937. It was that late. Okay.
And the disaster happened in New Jersey.
It was New. Okay. Google knows. So, it was in the Hindenburg. It's about 5 million cubic feet. How many moles of hydrogen is that? Assuming STP. This is a good review of how to do volume conversions because you've got cubic feet, and in order to use that conversion, the STP liters to moles conversion, we have to have it in liters. How do we get from cubic feet to liters? It's always your answer. What's our roadmap going to be? There's a couple routes you can go.
Beats sediment. Wait, what? Inches, it's inches. I don't remember. I'm sorry.
And then now what we've added today is at STP, we can go from liters to moles. You could also go if you wanted to go a different way, you could take cubic feet. Yeah, there's not really a better way. That's probably the best way. You could take cubic feet and go to cubic miles, and then cubic miles to cubic kilometers, and then cubic kilometers to cubic centimeters, but you still got to get to cubic centimeters at some point. Actually, I think you have a conversion that goes cubic meters to liters directly, but that's not going to save you any time. How do you go from cubic feet to cubic inches?
1 foot. 12 inches cubed. Wait.
No. We're going to cube the whole thing because the 1 gets cubed and the 12 gets cubed as well. There is a conversion, an exact conversion that goes cubic inches to cubic feet, but I don't know that number. But I do know 12 inches in a foot, and I know that I can cube that on my calculator.
Wait.
Because what happens when we cube this entire conversion factor? Everything gets cubed on the inside, right? So you can't just say 1 cubic foot is 12 cubic inches. It's 1 cubic foot is 12 cubed cubic inches. And then we can say 1 inch is 2.54 centimeters. Whole thing cubed. You did this, right? Okay. It's just been a while, probably. We haven't had to deal with volumes in a while.
Just back in the day.
We did the gas laws last year, was struggling with converting to, where it was gonna be.
That's true.
Who is that? It wasn't. Those are.
Once we're in cubic centimeters, what's our conversion?
Centimeters.
Centimeters cubed. And what is that? How many centimeters cubed is a liter?
10. That's my.
1,000. So let me rethink how I'm writing this. 1 cubic centimeter is 1 milliliter. So 1,000 cubic centimeters is 1 liter. And then because we're at STP, we can say Stone Temple Pilots. STP, I used to have to qualify it with, unlike that post-grunge band from the 90s, but nobody knows who STP is anymore. So I don't have to say that very much anymore. Stone Temple Pilots was a post-grunge band about 94 to 98 or so. They were big. Dead and Bloated. Plush. Whole album, their whole first album was actually pretty good, actually.
And it's like black.
All right. Reasonableness check. 5 million. Call that 1,000. Because I'm not going to cube 12 in my head, but I can cube 10 in my head. 5 million times 1,000 is 5 times 10 to the 9 now. Times about another 10. We're at 5 times 10 to the 10 now. Divided by 1,000. So 5 times 10 to the 7 now. Divided by another 20. So 2.5 times 10 to the 6, 5. 2.5 times 10 to the 5 or so. Should be somewhere in the 250,000 moles range. Ballpark. If you're not getting that answer, you may have forgotten to cube something somewhere. All right, I'll be back on Wednesday. You're gonna measure R.
You know, so you can say, that's black white.
Oh.
Is that